Hello, all. So today we are going to be looking at the limit definition of the derivative. I'm going to start by writing down our limit definition of the derivative, explaining where it comes from, and then I'm going to do a somewhat simple example to show you how we utilize it to find the derivative. So first, let's go ahead and write down that limit definition of the derivative. So let's have the derivative of some function f, so I'll write it as f prime of x. And our limit definition is that this is the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, I will point out, well, there's multiple different ways, like different notations that get used for this, but one of the popular ones is to use delta x instead of h. So delta x instead of h. The reason I like to go with using h instead of delta x is that all of these x's start to get confusing for my students. And so I just decided, you know what, I'm just going to use h and try to keep things as clear as I can. But hey, it's up to you or your instructor or whoever, right? Okay. Now, where does this definition come from? So let's go ahead and draw a xy plane, right? And some curve f. Don't really care what it looks like. I'm just going to draw some wiggles here, right? This is going to be f. So this is one of the main questions that was asked, which led to the development of calculus as we know it. So let's look at this curve. Let's think about it. I'm going to use the highlighter, I suppose. So notice at the beginning, it's increasing like quite quickly. As it reaches the top of this hill, it's not increasing or decreasing, right? Right at the top, it's not increasing or decreasing. Then it's decreasing pretty fast, right? Then doing nothing right at the bottom. Then it increases slowly, stops. I mean, it doesn't really stop, but it's not increasing or decreasing at this point. Decreasing slowly, increasing slowly, decreasing slowly, and then increasing fast again. So the question was, how could we determine how fast our curve is changing at a specific point, right? I want to know what the instantaneous change is at a specific point on the curve. And so let's just pick a point on the curve. I don't care where it is. I'm going to just pick, oh, how about just right here? That's fine. That's my point. And so for my x value, I'm just going to label that as x. And then what would my y value be? Well, it's whatever the function is evaluated at x. So the y value would be f of x. Right? Whatever we get when we plug in x into our function f. And what we want to know is, for this point specifically, how fast is it increasing at this specific point? Right? How fast is it increasing at this exact point on the curve? And this is where we draw what we call the tangent line. We're going to draw this line that just touches our point and is a representation of the instantaneous change at this point. So I'm going to do my best here. It should be a nice straight line. I know my drawing is so-so. There, that's pretty good. There's my tangent line. So this is my tangent line at the point x f of x. And so what's my question? What do I want to know? Right, what's the question that we're asking and that's going to lead us to this development of calculus? The question is, if I want to know, how fast is the curve increasing at this point, I need to know the slope of this tangent line. So I want to know, what's the slope of this line? What is the slope? So let's pretend you're a mathematician. This question has not been answered yet. And so I just have to use information that I already know about. Okay, I don't know the limit definition of the derivative. I need to use info that I already know, which I do have an equation for the slope of a line. So let's say the slope of some line L is y2 minus y1 over x2 minus x1. That should be familiar to you guys, right? That is the slope of a line. So this is my goal, is to find the slope of this red line. I'm going to erase this for now just to make room because I'm going to write some other stuff. So we should notice something here, which is that I'm going to need 2 points to get the slope of a line. So I need 2 points. Yes. Sure, sure, sure. So let's call this guy, this red dot, I'm going to write it down here. Remember, it's the point x, f of x. Let's call this our x1, y1 to use in the slope formula. And if I'm going to need another point to find the slope of a line, let's just pick something close to our point and we'll try to get like an approximation of the slope of the tangent line. So what if I pick, let's say, this point here? And so instead, we're going to find the slope of this line that passes through that. So notice it's not quite my tangent line. It's almost like we're going to try to get an approximation of the tangent line slope by finding this other line that passes through 2 points on the curve. All right, so now how do we label this guy? Right, so this is going to be at least at x, right? It's past that value x plus a little bit more. So I'm going to call that plus h, where h is the distance from my original x value. And so I'm going to put this in parentheses. You can assume then that h is like a small value, right? You would be trying to pick something close to your original point. So like generally speaking, h is small. Put it in quotations, small. Like there's no reason that you would pick a point like way far away on the curve. It should be pretty close to the original point that we're interested in. Okay, so then how would we label this point? Well, the x value is x plus h because it's just a little bit further away than x. That means my y value is whatever the function is evaluated at h. Yes, f of x plus h. And this is going to be my x2, y2 that I'm going to use in my slope formula. All right, so there we go. Now we have those 2 points that we needed, and we're going to go ahead and plug into the values into our formula for this slope of L. And this blue line is L. It's like an approximation of our tangent line. Okay, so let's fill in. So according to what I've written, y2 is f of x plus h, minus y1 is f of x, all over x2 is x plus h, minus x1 is just x. Again, I'm looking at these labelings that I wrote down in red and blue. And if we just simplify, we see that this x minus x will disappear. X minus x would just be 0, of course. And so I have f of x plus h minus f of x all over h. Okay, now we're getting somewhere, right? This is looking very, very similar to the limit definition of the derivative. The only part that I'm missing is the limit part. So let's discuss that next. So if we're thinking of this line L, that's my blue line, as being an approximation of that red line, how would I improve my approximation? How would I want to move this blue point to make the approximation better? Okay, well, let's think about it. The closer that blue point is to the red point, the better the approximation is going to be. So if I moved it a little bit closer, say to here, to make a new point, this green point, now look how close it is to my red line. It wouldn't be exact because it's still next to the red point, but it's getting closer and closer as I let my new point approach the original point. And so this new green point, would be like x plus h with a smaller h value, right? It'd be like x plus some smaller distance. And so to get the slope of my tangent line, sorry, wrong color. I'm going to use that approximation, which was f of x plus h minus f of x all over h. And I'm going to say, you know what? I don't want this to be an approximation. I want to get the real slope of the tangent line. And so what I'm going to do is I have this x plus h, where h is the distance between my original point and this new point that I'm utilizing. I'm going to take this blue point and I'm going to move it a little closer, right? H gets a little smaller. And then I'm going to move it even closer to the red point. H gets even smaller. And H is going to get smaller and smaller and smaller. That distance is going to creep down and down and down towards 0. And how do we write that mathematically? Well, we're letting h, that distance between the 2 points, we're letting it approach 0. And there you have it. This gives us the slope of our tangent line, I should say, at the point, that specific point, x f of x. And we use the notation f prime x. All right, now that we've seen where this limit definition of the derivative comes from and what it really means, which is that it's giving us this instantaneous rate of change at different places on the curve, depending, which point we pick, let's see an example. Right? Can't hurt to see an example and see this in action. All right, so I am just going to find just the old generic derivative f prime x if my function is, let's keep it simple, about x squared. Yes? All right, so right now, I'm not finding the derivative at a certain point because I haven't filled anything in for x. I'm just finding just the derivative, f prime of x. So it's going to be a function of x. We're not going to be plugging in a value yet. And I'm actually going to go ahead and draw the curve just so we can kind of, I don't know, discuss it or whatever. 1, 2, 3. Right. So we have a point that has a different color, but blue actually. So 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, and then 3 and 9, negative 3, 9. Wait, I got it right. Okay. So there's my parabola. Let's make it a little more curvy there. So let's think about what the rates of change would look like at different points on this curve. Again, to get a better understanding of what we are actually finding when we find the derivative. So right at the bottom, at this bottom point here, it's neither increasing or decreasing, right? It decreases down to this point and then increases after it, but it's not doing anything at this exact point. So here, the slope of my tangent line would actually be 0, right? It would be just this, gosh, I can't draw, but it would just be this flat line that passes through that point. So my slope of my tangent line at the bottom would actually be 0. Let's think about some other points and what you think the slope of the tangent line would be like. So this point, we see that it's increasing, right? So the slope of my tangent line should be positive, but maybe like pretty small because it's not increasing that quickly, right? Towards the bottom of our parabola, it increases slash decreases if you're on the other side pretty slowly. And so you're thinking that the slope of your tangent line would be pretty small compared to, say, this point where, look, it's increasing quite quickly. And so as I move further along my x-axis, so as I pick a point further along, we're thinking that the slope of our tangent line should be getting bigger and bigger and bigger, right? It starts to increase faster the further along the x-axis we go. All right, but for now, we're just going to use our limit definition of the derivative to find our derivative, not at a specific point yet. So we have f prime x. That's going to be our limit as h approaches 0 of f of x plus h minus f of x all over h. And so this is like a formula, right? We're going to have to fill in these values, or maybe not values, but fill in these expressions for the function that we're using. Now, some of my students kind of like to do their work off to the side instead of jumping into the definition right away. So we could do a little work over here. So what do we need to fill in to our limit definition? So we need f of x plus h, and we need f of x is going to get filled in, right? But f of x is just x squared. We don't have to do anything, right? Okay. But f of x plus h means I'm going to replace x in x squared with x plus h. So that would be x plus h squared. Now, the reason sometimes we like to do this off to the side is so that you can do a little bit of simplifying before I actually plug it into the limit definition. Let's actually square this. So we'll get x squared plus 2xh plus h squared. By the way, if you want to check me on that, this is x plus h times x plus h, and then you have to FOIL. Now I'm ready to go ahead and utilize my definition, and I should point out something that I haven't yet. We have this expression inside our limit, right? And we don't want to let h approach 0 yet. Okay, if we let h approach 0 right now, we're going to get the indeterminate form 0 over 0. And so you always want to kind of fill into the expression, do some simplifying before you actually let h approach 0. So let's go ahead and fill in. We don't really need the parentheses, but it's just to show you that the limit is acting on this entire expression. And so I have my limit as h approaches 0. F of x plus h is x squared plus 2xh plus h squared minus. Now we're going to be careful. Anytime you have a minus in like a formula, you should always have everything that follows it in parentheses because you might need to distribute the negative. So in this case, it's just x squared. But if there would have been more terms, I would have had to distribute the negative through them. So you just have to be really careful with that depending on what your function is. So I'm going to keep it in parentheses just because it's a good rule of thumb. All right. Once we've plugged everything in, we're going to go ahead and simplify. So we find that this x squared actually gets simplified and taken away, right? We have an x squared minus an x squared, and so we can get rid of them. Let's keep writing. Now, usually you could skip some little steps, but I'm going to try not to skip steps, assuming that maybe this is one of the first examples you've seen. All right, so I've done a little bit of simplifying. And as you simplify, you should be thinking, should I go ahead and let h approach 0? Have I done enough manipulation, enough simplifying with my expression? And just using my eyes, I see if I let h approach 0, I'm going to get a 0 in the numerator and a 0 in the denominator, so it would still be indeterminate. And so I don't want to do that yet. I'm going to see, is there anything else we can simplify? Well, I notice that every term in the numerator has an h, and every term in the denominator has an h. That means we could eliminate one of the h's, right? Now, a lot of my students like to say, all right, well, let's cancel one of the h's out. So they'll cancel this, cancel this. You don't want to make the mistake of canceling both h's here. You would subtract one from the exponent. So that's okay, but it does leave room for error, especially if you're kind of new to this. But this is what I would suggest doing. Let's do it the long way, which is actually the proper way, which is to factor an h out of the top and out of the bottom if necessary. So I'm going to factor an h out of the numerator. That'll leave me with a 2x because it only had one h available. And then an h to the first because there was two h's multiplied, right? Two h's available. Now you could factor an h out of the bottom, but it's the only thing that's there, so I just leave it as an h. And now we see that h over h is just 1, so we can go ahead and eliminate them. This is the same thing that would happen if I just said, oh, I'm just going to take away an h from each, right? We'd still end up with 2x plus h, but just leaves a little bit more room for confusion or error. So I'm not going to do it that way. And so now I have the limit as h approaches 0 of 2x plus h. And again, we'll think, does it seem safe now to let h approach 0? Sure, it does. If I let h approach 0, I'll get 2x plus h approaching 0, so 2x plus 0, and I just get 2x. All right, and that is not in indeterminate form. Nothing bad happens, and so we're happy, and we say, all right, this is our derivative, f prime. Very good. Yes, so we found the answer here. Now let's discuss what this means in terms of my function x squared. So I'm actually going to erase all this green stuff so I can write below my curve and decide if we think our answer makes sense. So don't forget what our derivative actually tells us. It tells us the slope tangent line at specific points on the curve. So we found just now that f prime x is equal to 2x. So this will allow me to find the slope of my tangent line wherever I want. I just need to pick an x value. So let's try a few and verify that we think our answer makes sense. So I mentioned, I'm going to do different colors. Let's do green for this bottom point. I mentioned that notice to the left side it's decreasing, then it gets to this point, and then on the right side it's increasing. So right at this point at the bottom, instantaneously, it is neither decreasing or increasing. When I get to the bottom of a valley like this or the top of a hill in a curve, my derivative should be 0. The slope of the tangent line should be 0 because it looks like this. It's truly just this straight flat line that passes through that point. So this is the point on my parabola, 0, 0. Let's check the slope of our tangent line. So slope of tangent line, I know I'm being extra specific, but slope of tangent line at the point 0, 0, meaning x is equal to 0. Right? So that would be my derivative evaluated at 0. That would be 2 times 0. And just as we suspected, my slope for this green line is 0. Because it would just be a flat line. All right, let's try another one, another point. I meant to write this all in green. Sorry about that, since the point was green. I'm gonna pick another color here. Let's do purple. No, orange. Now let's try this point, just 1, 1, 1. Yes, 1, 1. So what do we suspect the slope should look like of my tangent line? So my tangent line, oh, that was horrible. My tangent line looks something like this. And so my slope of my tangent line, it is increasing, like the curve is increasing. So the slope should be a positive number. Whereas if I was over on the left side over here, the slope would be negative. We should get a positive number. And I don't really have anything to compare it to right now. So as long as it's positive, I would like think the answer seemed accurate. So now let's find our slope. I'm going to be lazy here. Well, I'll write it. Slope of tangent line at the point 1, 1, meaning I'm going to plug in x equal to 1. So this would be my derivative evaluated at 1. That would be 2 times 1, and so I get 2. And so I find that my slope here is 2. I have no reason to think that that's a bad thing. I mean, it's positive, so that makes sense. And so I'm happy with my answer. Let's do one more. I'm going to use purple this time. This point is so horribly drawn here, but this point is supposed to be 3, 9. So this is my point 3, 9 on my parabola. And let's try to draw our tangent line. I know, I'm just horrible at drawing them, but there's my tangent line, and I want to know what the slope is. Okay, so now we have some things to compare it to. Again, this is an increasing portion of the curve, so I know that the slope of the tangent line should be positive. But not only that, it should be bigger than the slope of the orange line, right? As I move further along in the parabola, it starts increasing faster and faster and faster. So the slope should keep getting larger and larger as I move along. Okay, so let's go ahead and find the slope of my tangent line at 3, 9. Meaning what all I need to do is plug in x equal to 3 into my derivative. So that's f prime at 3. That would be 2 times 3, which is 6. And so I find that the slope of my tangent line here is 6. And now that we have some things to compare it to, we say, you know what? This all seems reasonable to me. The slope at the bottom was 0. The tangent line would be flat there, so that makes total sense. Then as I move along to the point 1, 1, the slope of the tangent line is 2. So instantaneous rate of change there is 2. And then I go further along to the point 3, 9, and my instantaneous rate of change is 6, which makes sense because it should be getting bigger as I move further along the x-axis for the parabola. Now, if you want to look at the other side, you're welcome to. If we move over to the other side, say to this point directly across from 1, 1, negative 1, 1, notice that the line would be the same, just reflected. So the slope here should be negative 2. Because it's decreasing at the same rate as it was increasing on the other side, but it's just, it's decreasing, so it's negative. All right, so I think we've covered plenty with this example, so I'm going to stop us there.